Okay, in this lesson we're going to have a look at how a Van de Graaff works and introduce the concept of electrical potential energy. Now, a Van de Graaff or a Van de Graaff generator is a machine that isolates charges. Now, it works in pretty much the following way. What you have here is a rubber belt. Okay, let's assume, for example, that the rubber belt is turning in this direction. Okay, so we've got a rubber belt, and the belt is driven by two rollers. Now, the rollers are made from different materials. Okay, we have usually a type of acrylic or polythene material here at the bottom, and at the top you might have, for example, a glass or metal roller. Now, as the rubber belt passes around this roller, what we have here are brushes, which are kind of sharp pointed conductors which are not actually touching the belt, as is the same here, but they're very near to the belt. This one sucks negative charges or drains negative charges away from the belt. Now, as a result of that, that leaves the belt charged positively as it's coming up here. Right? So the negative charges have been drained off of the belt, leaving it positive here as it comes up around the roller at the top. And as this happens, then negative charges will be drawn from the dome to cancel the positive charges on the belt. Okay, so negative charges will be drawn from the dome. Okay, they cancel the positive charges, but that will leave the dome conductor charged positively. So the effect of passing the belt round and round the two rollers is to isolate positive charges on the conducting dome. We don't really need to worry too much about the ins and outs of this mechanism. What is important here is that positive charges are isolated on the dome. And whenever like charges, whether they're positives or negatives, accumulate together in one place, then we increase what is called the electrical potential energy. Now, you've come across this already when we looked at the unit on energy. So electrical potential energy is energy that is stored. So effectively the dome becomes a store of electrical energy. And as in the case of any type of potential energy, that energy is invisible. We cannot perceive it with our senses, but it is there. Now, the next thing we're going to say might sound quite surprising, but the electrical potential energy stored in this dome is actually quite large. In fact, typically you could say that the electrical potential of the dome is well over 50,000 volts. Now, that might seem quite a large number to you, but actually it's not a dangerous situation, not really, because the amount of charge gathered on this dome, even though it's stored at a very high electrical potential, the amount of charge is actually quite low. Now, I'll talk about what that means in a minute. Now, if you want to become aware of this electrical potential energy stored on the dome, then we need to change the configuration of the Van de Graaff slightly. In fact, what we're going to do is we're going to connect another smaller dome here to the earth socket. So let's just make a note of this. This is the earth socket. Now, whenever you connect a conductor to earth, okay, then its electrical potential becomes 0 volts. Now, what we now have here is one dome at 50,000 volts, and that is quite near to another dome at 0 volts. And the electrical potential difference between the dome and the sphere is Okay, 50,000 volts. So one electrical potential is 50,000 volts minus the other electrical potential is 0 volts, which is equal to 50. And it is this electrical potential difference that causes the spark to jump between the spheres. Okay, let's imagine this situation then. We turn on the Van de Graaff generator, and as a result positive charges will start to accumulate on the surface of the conducting dome. The electrical potential energy stored on the dome starts to increase, and typically that will reach equal to or over 50,000 volts. Now these charges are being stored on the surface of the dome. We're not really aware that they are there. This is electrical potential energy. Now we want to observe electricity flowing from one place to another in the form of an electrical current. Then we have to create an electrical potential difference. Okay, and what we're going to do that is we're going to connect, for example, this dome going to connect the Van de Graaff dome like that, for example, to an ammeter. Right, this is an ammeter, and the ammeter measures the flow of electrical current. Okay, it measures current, and the other terminal of the ammeter is going to be connected to a metal conducting tap. We remember that taps act as good electrical earths because the tubing in a house or in your school will be made of copper, which is a good conductor, and that copper will eventually feed through to the ground underneath the building. Okay, so taps are a good source of earth, so that we can make a note of that. We can just write in the earth sign here. That symbol means that the tap is earthed, and when an object is earthed, then its electrical potential is 0 volts. So we have created here an electrical potential difference between the dome at 50,000 volts and the tap at 0 volts. Now it is precisely this electrical potential difference that pushes an electrical current along the conducting wire. Now there's an experiment in the watch and learn section on charge and the Van de Graaff in which we set up an experiment similar to this. The important point to note is that the ammeter that we're using is a very sensitive ammeter, because the current, the electrical current that flows between the dome and the earth is actually very, very small indeed. You're talking about 10 or 20 microamps. Right? And a microamp is a millionth of an amp. We can make a note of that, for example. So typically the current that's flowing along this cable is typically, say, 20 to 50 microamps. That's a very, very small current. So although the voltages involved in Van de Graaff generators are very, very big indeed, the currents that are produced are actually very small, because, as I said earlier, the amount of charge that gathers on this dome is actually quite small indeed.